We perform the task of parametric scene parsing from ground and aerial imagery. For example, from this pair of ground and aerial imagery, we can infer that the main road has two lanes. Sidewalks to the left and right. Crosswalks before the intersection and right of the intersection. Side roads to the left and right of the main road. Distance to the intersection is 28.1 meters. And the width of either side road is 7.4 meters. Prior works addressing this task use ground imagery as their only modality. However, by relying only on ground imagery, these works are limited by perspective foreshortening, occlusions and narrow field of view of the camera. By looking from the bird's eye view, aerial imagery has the advantage of presenting a uniform resolution for distance and semantics estimation in both the near and far fields, avoiding severe occlusions due to traffic, and affording a larger field of view. However, aerial imagery cannot observe all local properties of the road accurately, due to occlusions and building shadows. Ground imagery, on the other hand, provides strong visual cues for the measurement of local properties. We leverage the complementary properties of ground and aerial modalities to provide an accurate representation of scene geometry and semantics in unconstrained traffic scenes. In the remaining part of the video, we demonstrate the complementary properties with illustrations. We start by showing that the unified model performs better than the proximate model on attributes that rely on global context by comparing performance on distance to intersection. The bar graph compares the performance of our proposed unified model, which uses both ground and aerial modalities, against the proximate model, which uses only ground imagery on distance to intersection. The ground truth values are shown here for reference. At the top of the bar graph, the mean absolute error for the unified and proximate model is shown. The proximate model by itself leads to higher errors due to perspective foreshortening. Our unified model is more accurate, as the aerial imagery has a uniform spatial resolution for distance estimation. We show another example where the same behavior can be observed. We now show examples where our unified model performs better than the remote model on attributes that rely on local properties. First, we compare the performance of models on predicting if the main road has two-way traffic or not. The bar graph displays the confidence of our unified model and remote model, which uses only aerial imagery to predict if the main road has two-way traffic. If the confidence is high, then the model is inferring that the main road has two-way traffic. The remote model by itself predicts incorrectly, as it cannot perceive vehicle direction. Our unified model predicts more accurately due to higher spatial resolution of nearby vehicles. We now compare the performance of models in predicting the presence of a delimiter on the main road. Remote model by itself predicts incorrectly, as the delimiter occupies only a few pixels in the aerial image. Our unified model predicts more accurately, as the delimiter is clearly visible in the ground imagery. Thus, in our work, we exploit the complementary properties of both aerial and ground modalities to derive a more accurate representation of scene geometry and semantics in unconstrained traffic scenes.